just hydrophilic. And so you just have to apply these extreme conditions, like the Li2OHCl, the partially dehydrated form, is just extremely stable. So to remove that last little bit out, yes, as you said, when you have to induce so much phase transformation to get it to the dehydrated Li3OCl stoichiometry in phase. Yes, there's a whole lot more to say on that, but given that it's relatively new, I don't want to go into it as much as the other compounds. So, okay. Right. So this section I call sustainability, but I've also named it critical elements in circular economy, because that's what it really comes down to, right? Where it really just comes down to sourcing, the drive of both substituting out cobalt for lithium-ion battery cathodes, right? And also going to technologies like sodium-ion batteries or lithium sulfur batteries or lithium air. It's really all to reduce our dependence on critical elements, obviously engineering higher capacity and also higher voltage materials are objectives, but the target there, the underlying reason is really avoiding critical elements, but also critical elements that swing, with the geopolitics of like whatever's happening today. And then we'll wrap up the discussion of lithium-ion batteries as it pertains to the circular economy. Electric vehicles are, in terms of at the consumer level, have been more accessible than ever, and it continues to be more accessible as the years go on, right? And quite a number of projections predict that as early as 2030, 2040, depending on which continent you're on, there will be parity in terms of the number of electric vehicles sold versus the number of gasoline-powered vehicles, right? So obviously, the numbers are there. The data is there, the modeling is there to tell us that this is something that we should be concerned about. This is the circular economy of batteries is something that we need to actually have a strategic plan for. So in terms of asking the important questions, other than should we recycle things, that's kind of vague, but more specifically, which materials are we targeting? What are the standard metrics for quantifying sustainability? Because just because one labels something as sustainable, there has to be some scientific data behind that, because otherwise you run into the concept of greenwashing, right? Just because you're recycling something, that concept doesn't actually make justifiable sense in terms of energy consumed to recycle the material to begin with. And in terms of the recycled material, is that recycled material going to perform at the level of the pristine as prepared material to begin with, right? So we're going to try to put some sort of standard metric for the discussion and quantification of quote unquote sustainability, so we don't, become wish-washy, like hand-wavy type of discussion. And then of course, we also need to talk about, what timescales are we going to have to deal with for lithium-ion batteries? The life cycle of going from mining and sourcing the elemental, the precursors, the oxides, sulfides, purification, and then going to fabrication. And then the possibilities for recycling batteries themselves, not just going back to the the starting materials of the oxides or even the metals to become oxides. I'm talking about, just taking a battery and then reusing it for another purpose, because that's also a viable option, right? So we don't always have to go back to the as prepared material, because it might not be energetically reasonable. So that's the foreshadow for you. Okay, I just gave away the punchline. So yes, in terms of sustainability, I think it is assumed that one should care about sustainability, but when it comes down to it, really, it is about economics, right? The consumer will only care about sustainability if it makes sense in their budget. You cannot convince someone to spend more if it means less money for them, today, because we all have to pay bills. We all have, our lives to, food to buy, things like that. So it is an economics issue. And I think just dictating that one should care about sustainability really doesn't take into account people's lives, and the realistic conditions and the lives that people lead. So we have to have an argument that has a core and a foundation of numbers and dollars. Okay. So I will start with that. So let's talk about projections. Why should we care about sustainability today? Mainly because all the projections tell us today, the future is very close to today, right? If you talk about carbon capture and storage, sometimes the length scale is like 100 years. You capture carbon or CO2 from the atmosphere, you store it underneath, the ocean or in whatever tanks you want to store it in. Those are 100-year time scales. We don't really have 100 years, especially if your containers are going to leak at 1% a year, which it will, by the way. Then in 100 years, you have a problem, but you don't have 100 years, right? You have to start producing these containers before 100 years. So how many years do you really have? I mean, we have the same problem, except energy storage is not 100 years. So if you look at this projection, this is 2022, okay? So we're here. The projection is that in terms of the global number of vehicle sales in millions per year, you can see here by 2040, most of them will be electric battery-based vehicles, okay? But that means the technology that's developed today will affect the manufacturing line like 10 years from now, which will be 2032, and 2032 is 8 years away from 2040, right? So it's not that far away where we actually really have to think about what happens when more cars have batteries and lithium-ion batteries in them than not. Okay, so these numbers, so any little bit in terms of percentage that you can adjust for critical materials dependent will have a very huge impact. So I did this sort of back of the envelope calculation that you see here, which I call the Fermi calculation, because Enrico Fermi is notorious for doing these types of calculations, where if you look at the Argonne National Lab BAT-PAC3, so battery performance and cost analysis 3.0 model, they've been doing this for a very long time, right? So if you look at using some of these, base numbers, if you have a single car that uses current technologies of NMC, so nickel, lithium, nickel, cobalt oxide in 5 nickel, manganese, cobalt 532 ratio, right? A typical car in a pack will have 8 kilograms of lithium, 35 kilograms of nickel, 20 kilograms of manganese, 14 kilograms of cobalt. So how do these values scale? Let's say we keep with NMC 532 technology. Let's say NMC 622, NMC 811, current developments, just all disastrously fail. We can't make it work. We're going to stick with NMC 532. That's the going assumption. By 2040, we have to make 60 million new cars, like each year. So how many years is that going to last us? Well, first we need to know, well, how much of the raw material do we actually need? For lithium, usually it's lithium carbonate, that's sourced from brines. If you have 8 kilograms of lithium per car, and you need 60 million cars, because that's the projected sales growth, then you need 480 times 10 to the 6 kilograms, right? Some pretty basic algebra, actually arithmetic here. So by analogy, you're going to need the same order of magnitude, nickel, cobalt, and manganese. All right, so now you have a feel of the magnitude of just the sheer amount of elements, the mass of each element that we need. Okay, and that is vastly different than our discussion of materials now, because look at the number of kilograms of metals in each vehicle if it's a conventional gasoline powered car. You see here copper and manganese. Now, what's not featured here, because it's just not discussed in this particular paper, is a discussion of aluminum, iron, steel, and iron. Okay, so that is not discussed because they're just trying to focus on, you know, the more critical elements like lithium, nickel, manganese, cobalt. Although I should say critical as in important, not critical as in the technical definition of what a critical element is, which we will discuss in a few slides. Okay, so right now, or at least 2 years ago, right, 1 million cars were sold, at least in the US. Now you're going to ramp up to 60 million cars globally. And we do actually have to care about what's happening globally, because Europe, by 2030, if their proposed bill goes through, that means all of the cars that they're going to sell by 2030 will be electric, right? So this has huge ramifications very quickly. That's 8 years from now, by the way, right? So that's the urgency, and those are the quantitative metrics. So if you dig up the US Geological Survey mineral report, the mineral commodity surveys, they have one for every element. You can see, you can ask yourself, are we going to have an issue producing, mining 10 to the 6 kilograms of materials, period, in the US and also globally? And where are we going to get these materials from? So if you look at the raw element, I should say it comes out as both metal, lithium comes out as both metal and carbonates. Those are two major sources from brine. So when I say material, I really mean the element. If you look at lithium, USGS survey says we're not really going to be short on lithium, right? There are 750 1,000 metric ton in reserves. So in terms of production from 2021, you could see the countries that are producing this material that we source from is going to be Australia, it's going to be Chile, and also China. So those are the major players when it comes to lithium production, right? So the lithium brines that we do have in Nevada and also the Salton Sea, they do not compete as much, in terms of who we're buying, lithium from. These are the countries. So now you have a sense of the geopolitics that are going to come into play whenever you have non-domestic products. Okay, so if we said, okay, well, the lithium global reserves, that means it hasn't been mined, but lithium is there for us to mine, is predicted to be 22 million metric tons. Okay, but we need, from what we calculated before, 4.8 times 10 to the 8 kilograms. So I converted from 480 to 4.8 to be more scientifically correct using the scientific notation. So what that means is then if our reserve is 2.2 times 10 to the 10 kilograms, and by 2040 per year, if we continue to sell, if people continue to buy at the rate of 60 million electric vehicles a year starting from 2040, if that rate remains the same, our lithium reserve will last 45 years. Without any recycling, if we just keep on sourcing lithium from the earth, we have 45 years worth of lithium. That's what we're dealing with. So that it could be significant or not. You'll probably be close to retirement, so it might not matter for you. If you are thinking about, having offspring, it might matter. It might not, depending on your viewpoint, who knows? But that's all to say, objectively, we have 45 years based on these projections, right? So 45 is a long time. It does give us a little bit of time to think about how to recycle and source lithium so that we don't completely deplete what's available, okay? And then in terms of looking at the metals for the 2021 production line, you'll see here that, let's see, we need 10 to the 6th, 2100, just about between 1,000 and 2,000 million kilograms of each metal. So you could see here that it's really more critical that we corral our discussions around the metals. The lithium reserve is not the issue. It's this. Okay, the reserves are just not that much. On top of that, mining conditions are a whole nother, discussions for how we get these elements out. Not only mining conditions in terms of humanity, but mining conditions in terms of energy, how much energy it takes to get these elements out, because they don't always come out as metals. They come out from co-refining other metals because they're not in ores by themselves. Okay, so the purification step is actually what's going to be an issue. In terms of looking at some of the other chemistries, because we talked about lithium iron phosphate, we've also talked about using either lithium metal or graphite, or the current collector copper. When we look at the countries that where the global reserves really are, you can see here, a lot of them are not the US. Okay, so diplomacy and international relations really play a key role in our discussion. And when I say humanity, I also really mean, what do the people of Chile want? Have we asked them? And in terms of, renting out, a mining company renting out, space of the brine to then manufacture, it brings money, it brings dollars, or sorry, it doesn't bring dollars because Chile is not on the dollar, but it does stimulate the local economy. But is that always in the best interests of the local people? And it's not always clear to me that those voices are being heard. It's clear to me that the mining companies are being heard very well. Okay, so there's a lot of factors that come into play when we talk about sourcing and designing, raw materials. Okay, but I also included this slide just so we're all on the same page, in case you don't think about electric vehicles every day. Certainly, the terminology also could change a little bit depending on the context that you're talking about. So I wanted to be clear when I say a pack, what I really mean. Okay, so we're all familiar with the discussion of the cell itself. That's what we've been talking about, the components of a cell, one cell. But these materials all really have to come into play when we start talking about, in the thermal management as well, when we talk about, assembling these individual cells into a module that will eventually go into a pack. That, of course, will be a part of the electric vehicle. And you could see here that once you assemble these packs or the modules into packs, regardless of the types of cell that you start off with, cylindrical or prismatic or pouch, the three most popular, you could see that the battery itself becomes quite an integral structural component of the car itself, right? In terms of mass, in terms of the space that it takes up. So then added to the sustainability discussion is not just the cost of raw materials, but also now a design component where the integration of these batteries really have to come into play when it comes to anticipating things like accidents and how these batteries, the structural integrity of these batteries need to hold up. But on top of that, if they're still using liquid electrolytes, then the flammability component is an important factor. Okay, so that's what I mean when I say pack, is the entire 7,000-8,000 single cells typically. That's what I'm talking about. Okay, when I talk about pack. Now I've said before, in terms of sustainability, there is an argument that costs will drive the increase of the adaptation of electric vehicles in society. And we see that by just looking at the raw cost of materials, because the raw cost of materials will also significantly impact the cost of the battery, which will then impact the cost of the car. So in terms of, the cost here of these major chemistries, so for the cathodes, right, LMO, LFP, yada, yada, NCA, all the NMCs, right? The price from 2010 going to 2018, which is already 4 years out of date, you could see the prices are decreasing in terms of per kilogram of these compounds. So it's more accessible now in terms of driving down the costs of electric vehicles, which is generally a good thing. And that's really across the board for all the other components as well, in terms of synthetic graphite, LTO, even, lithium titanate, the electrolyte, I mean, everything in terms of the scale up of production is driving down the price. And also the engineering of the battery so that they're more efficient as well. So they last longer, and thus the battery cost will also go down. Okay, so far so good in terms of increasing accessibility to these electric vehicles. But overall, what we need to talk about is it worth it? What chemistry is really worth it to push if we're talking about sustainability point of view? And the quantitative metric that the community adopts in terms of quantifying these discussions is the life cycle assessment, right? So what LCA does is it quantifies the energy and the materials that are used and the emissions and waste over the complete life cycle chain. So it starts from where the raw materials are coming from. We start with lithium carbonate for lithium ion based cathodes, and even lithium metal based anodes, and we go all the way to manufacturing, and then at the end, what do we do with that? So how much energy does it take? In terms of fabrication, it's going to take electricity to fabricate the batteries, and some of the conditions for fabrication of the pack, and then assembly into the car, and then also recycling takes natural gas. So that has to be taken into account as well. The energy that we use, it's just not all electric based, right? So all of that, all of those conditions, all of those assumptions go into a standardized list that you see here. And this is a typical model. It is not the only model. And that is something that one has to take into account when discussing life cycle assessment. If you look up the literature on life cycle assessment of lithium ion batteries, you'll see that there are a number of models out there, and you just have to pick a lane. You go with one if you agree with their assumptions, but usually they'll list all the assumptions that are there. But most importantly, in these seven, in this list of 7 in the life cycle assessment, you'll see that it takes into account the raw materials, the extraction, the bottlenecks in the supply chain. So we've seen a little bit of that already from the metals that we're talking about. And just as importantly, the quantification of environmental impacts, right? So it's not just, it's difficult to quantify environmental impact because you don't always see the environmental impact. And even then, it's not clear what the source of the environmental impact is. So life cycle assessment tries to pinpoint exactly that by denoting all these factors that we'll talk about, like climate change. What is climate change? Okay, increases in global, in greenhouse gases, but different greenhouse gases have different impact on global warming. So we have to normalize the data in some way. And so these are all the units that people typically use in their life cycle assessment. So the release of CO2, let's say during the purification from the ore to the metal, If it also produces methane, then methane has what 10x the global warming potential of CO2. So 1/10 of methane that's released is the equivalent of 1 mole of CO2 that's released. So that's the normalization strategies that are implemented here, right? So it's all built into these models. And then, more down the line would be, really identifying what's the most energy intensive part. Is it the mining? Is it the sourcing? Is it the fabrication? You can discuss that in terms of energy. You can also discuss that in terms of the costs of labor. Is mining the most difficult part, or is the fabrication of the battery, the labor of that, the most difficult part? And how do you streamline that then? So that's what people talk about when they, talk about analyzing what's energy intensive. And then the rest, I would say, is a lot of modeling. Well, it's already a lot of modeling to begin with, but when you say, okay, I'm going to mine 1 kilogram of lithium carbonate out, you can sort of see where how much energy it's going to take to convert like lithium carbonate to lithium. But then down the line, how do you quantify environmental impact of net flows? That's really that's more challenging, right? But we'll talk about that. So in terms of the overall picture, I like this diagram because it really summarizes the process, the life cycle of the batteries that we're going to talk about. We've talked a lot about the raw materials, and we'll continue to talk about the raw materials because it's where the energy materials design component is. But down the line, in terms of cell manufacturing and then actually fabricating the pack and then assembling into electric vehicle requires as much study and efficient engineering as the material design itself. And then the recycling, right? How do we recover the spent material? Once a battery is deemed non-functional or more colloquially dead, what does that really mean quantitatively? It may not be usable for its primary function, but how can we reuse it? And should we reuse the battery, or should we try to recover the material? So these are the methodologies that are typically employed to get the material back in its pristine form. So all of this goes into the life cycle assessment. Okay. And of course, there's also just landfill, throwing it in the trash, which you don't do with lithium-ion batteries, by the way. So next time, we are going to pick up on the discussion of sustainability by discussing the critical materials that are in the batteries. So with that, we're going to adjourn for today.